stress, hints of wear, indications that systems are operating close to their limits. They have run computer models simulating Flight 14's more demanding profile, checking whether the structural margins are sufficient, whether the fuel reserves are adequate, whether the thermal protection will survive the more intense re-entry. The systems passed every check. The models predicted success with acceptable margins. And critically, the team identified no showstopper problems, no fundamental flaws that would prevent attempting an orbital mission. The preparation for Flight 14 is proceeding in parallel with the data review. Booster 21, the vehicle that will power the mission, completed its cryogenic proof tests, where engineers fill it with liquid oxygen and liquid methane at the temperatures and pressures it will experience at launch, and verify that every system functions correctly. Ship 41, the upper stage, receiving its engines. Following the trajectory of previous vehicles, engineers expect to conduct a static fire test of Ship 41's engines about 3 weeks after the engines are installed, validating that all 33 Raptor 3 engines can ignite and run together in harmony. If that test succeeds, the vehicle will undergo final integration, final inspection, and final validation before being transported to the launch pad. The timeline is aggressive. SpaceX is targeting a launch window in the third quarter of 2026, which means August or September. This represents only a few months from Flight 13 to Flight 14, a rapid cadence that would have seemed impossible a few years ago. But SpaceX has learned how to move faster. With recent improvements to the launch infrastructure, with better understanding of how to inspect and maintain Starship systems, with streamlined processes for engine installation and testing, the company is approaching the goal it has talked about for years, launching Starship on a monthly basis. Flight 14 might be that moment when the goal transitions from aspiration to reality. The Tower Catch itself represents an engineering achievement that deserves attention. The Mechazilla arms are not simple mechanical grabbers. They are sophisticated systems with their own guidance computers, their own sensors, their own hydraulic systems. They must catch an object that is 50 meters tall, weighs nearly 200 tons, and is traveling at supersonic speeds. The margin for error is measured in centimeters. The timing must be perfect. The closing speed must be controlled precisely to avoid damaging either the arm or the spacecraft. Miss by a few meters, and the vehicle crashes to the ground. Miscalculate the timing by a fraction of a second, and a collision occurs. SpaceX has practiced this maneuver with the booster over a dozen times, and the success rate has climbed steadily. But the upper stage presents different challenges. It enters at higher velocities. It experiences different aerodynamic forces. The guidance system must be more responsive, making real-time adjustments to account for the vehicle's behavior during descent. What is perhaps most remarkable is that despite this extraordinary ambition, despite planning a mission that pushes every envelopes, SpaceX remains cautious about one thing. They will not attempt to catch the booster on Flight 14. Booster 21 will launch, deliver its cargo to the upper stage, separate, and return for a soft splashdown in the Gulf of Mexico. This is intentional. Catching both the booster and upper stage on the same mission would be taking on too many untested variables simultaneously. Better to perfect each component separately. Catch the upper stage this flight, then work toward catching both on Flight 15 or 16. It is a calculated progression, ambitious but not reckless. The Starlink V3 deployment component of Flight 14 adds another layer of complexity. These are not inert satellites that SpaceX will simply eject from the vehicle and abandon. These are active spacecraft with their own guidance systems, their own propulsion, their own communication equipment. When they are deployed in orbit from Starship, they will unfold their solar arrays, activate their thrusters, and attempt to maneuver into position. Then, while Ship 41 is still in orbit, while both the satellite and the spacecraft are moving at 17,500 miles per hour, they will attempt to establish laser communication links. This is unprecedented. No spacecraft has attempted to deploy and connect to a constellation while operating at orbital velocity from an orbital stage vehicle. If it succeeds, it opens possibilities for rapid satellite constellation updates and maintenance. If it fails, it provides crucial data about what adjustments are needed. The selection of V3 satellites for this deployment is also significant. Starlink V3 represents a major technological advancement over previous Starlink versions. These satellites are larger, more capable, and equipped with more powerful communication systems. They carry more advanced laser communication equipment for intersatellite linking. They have more propellant for maneuvering. They represent a significant investment by SpaceX in next-generation space infrastructure. Trusting them to Flight 14 when there's always a possibility that the mission could fail demonstrates confidence in both the Starship vehicle and the decision-making process behind the mission profile. The regulatory approval process for Flight 14 is also worth noting. The Federal Aviation Administration, which licenses all commercial spaceflight activities in the United States, must approve not only the basic launch, but also the expanded landing zone profile. For previous flights, both the booster and upper stage splashed down in ocean areas relatively close to the Texas coast. For Flight 14, the booster will splash down in the Gulf of Mexico as before, but the upper stage will attempt a tower catch at the launch site. This means the vehicle will be descending through the atmosphere over populated areas of South Texas before the final minutes of flight. The FAA must assess the safety implications, determine that the probability of debris falling on population centers is acceptable, and issue the license accordingly. This typically requires environmental assessments, hazard analyses, and coordination with local authorities. SpaceX expects FAA approval ahead of the final launch preparations, but it remains a potential constraint on the mission timeline. The implications of Flight 14 extend far beyond SpaceX and Texas. NASA has contracted Starship as one of 2 vehicles to deliver astronauts to the lunar surface as part of the Artemis program. The first crewed lunar landing mission, Artemis III, is targeted for 2027, though that timeline faces increasing scrutiny. For Starship to carry astronauts to the moon, it must first prove orbital operations. It must demonstrate reliable orbital rendezvous and docking. It must prove in-space propellant transfer, the technology that will allow it to assemble the full fuel load required for a moon mission. Flight 14 is not directly testing in-space refueling, but it is testing many of the systems and techniques that will enable it. Every successful system on Flight 14 moves Starship closer to being ready for crewed lunar missions. Plans change. In the aerospace industry, where every mission costs hundreds of millions of dollars and the margin between success and catastrophic failure is often measured in milliseconds and pounds per square inch, the ability to adapt, to scale ambitions up or down based on what you learn, is not a luxury. It is a requirement for survival and progress. SpaceX learned this lesson years ago, and it learned it the hard way. But the organization that emerged from those early failures developed a culture of flexibility, of rapid assessment, of the willingness to attempt something far more audacious than originally planned if the opportunity presents itself. This philosophy is about to be tested like never before. After 13 suborbital test flights, after years of incremental progress, after proving again and again that reusable rockets are not merely theoretical but operational reality, SpaceX has made a decision that will redefine what Starship Flight 14 represents. It will no longer be a tower catch attempt. It will be humanity's first attempt at something far more profound. The first orbital flight of a fully reusable super heavy lift launch system designed to recover both stages and deploy operational payloads. To understand the magnitude of this shift, you must understand where Flight 14 came from and what it was supposed to do. For months, the plan was straightforward. After Flight 13 demonstrated that Starship could survive the extreme temperatures and pressures of suborbital reentry, Flight 14 would launch, ascend, and then attempt something no orbital-class spacecraft has ever successfully accomplished, catching the upper stage in the mechanical arms of the launch tower during its final descent. The Super Heavy booster had proven this capability multiple times. It had launched, climbed to altitudes where the sky fades to black, separated from its upper stage, and returned to land itself back in the mechanical grip of the tower arms at Starbase. Every successful catch was proof that the concept worked, that robots could grab a rocket from the sky at hypersonic velocities and bring it safely back to the launch pad. But catching the booster and catching the upper stage are not equivalent challenges. The booster travels relatively slowly during recovery, having expended most of its fuel during ascent and still retaining significant structural integrity. The upper stage is different. It has to climb higher, accelerate faster, and endure re-entry at near orbital velocities, approaching 17,500 miles per hour. The thermal stresses are immense. The structural loads are severe. The aerodynamic forces are extreme. Attempting to catch such a vehicle requires precision guidance, real-time trajectory adjustments, and a launch tower system capable of withstanding impacts from an object, traveling at speeds that would incinerate most materials on contact. SpaceX engineers knew this would be extraordinarily difficult. They prepared for years. They built the systems. They modeled the dynamics. Flight 14 was to be the moment of truth. Then Flight 13 happened. On July 24th, 2026, Starship Flight 13 launched from Boca Chica, Texas, carrying a payload of 20 Starlink version 3 satellites. The mission profile was suborbital. The vehicle would climb, reach maximum altitude, deploy the satellites for testing, then return through the atmosphere and splash down in the Indian Ocean. But something remarkable occurred. Flight 13 did not just complete the mission, it validated every system. The new thermal protection tiles worked perfectly. The landing flap actuators performed flawlessly. The guidance and control systems proved more responsive than predicted. The ship descended through the upper atmosphere, transitioned through the sound barrier, continued downward, and splashed down intact in the Indian Ocean. It was a perfect demonstration of everything Starship needed to do to operate safely in space and return reliably. More importantly, Flight 13 revealed that the vehicle was ready for more. The data told the engineers that the systems were mature, the hardware was reliable, the software was performing as designed, and critically, the margins, the buffers built into the systems to account for uncertainties, were larger than expected. This means that Flight 14 does not need to be a cautious repeat of Flight 13 with a tower catch attempt. It can be something far more ambitious. It can be the next quantum leap. Elon Musk, in the hours after Flight 13's successful splashdown, made the announcement. Unless problems emerged in the detailed review of Flight 113's telemetry, SpaceX would attempt to catch Starship's upper stage on Flight 14. But he went further. The mission would not simply be a suborbital test followed by a tower catch. Flight 14 would attempt something that has never been done before. It would send Starship to orbit, not on a test trajectory that touches the edge of space and returns, but on a full orbital trajectory where the vehicle climbs to orbital altitude, completes the velocity burns required to enter orbit, and then executes a controlled return from actual space. The implications of this decision cascaded through every aspect of SpaceX's planning. Flight 14 is no longer a single objective mission. It is now a multi-objective mission of extraordinary complexity. The vehicle will launch with both the booster and upper stage. The booster will return for a tower catch at the launch site. The upper stage will continue to orbit. While in orbit, it will deploy additional Starlink VV3 satellites. But not just deploy them passively. It will attempt to link them to the existing Starlink constellation via high-capacity laser communication systems, while both are in motion in zero gravity. After completing these tasks, the upper stage will execute a controlled deorbit burn, begin its descent through the atmosphere at the extreme upper end of possible velocities, and attempt to land itself back in the mechanical arms of the launch tower at Starbase. This sequence represents perhaps the most ambitious test flight in the history of spaceflight. If successful, Flight 14 will prove that Starship can operate as a genuine orbital system, that it can deploy real payloads to real orbits, that both stages can be recovered and reused. It will demonstrate that the dream of rapid, routine access to space, the foundation of SpaceX's entire vision, is achievable. If it fails, if any single element breaks down, the consequences are spectacular and expensive. The vehicle will be lost. The payload will not reach orbit. The tower catch will not occur. But SpaceX has decided that the potential payoff justifies the risk. This decision to escalate is not reckless. It is grounded in data. Flight 13 provided thousands of hours of sensor recordings, pressure measurements, thermal data, and structural telemetry. Engineers have spent weeks analyzing every millisecond of that mission, looking for signs of. The broader space industry is watching Flight 14 with intense interest. Traditional aerospace contractors, international space agencies, and commercial spaceflight companies are all paying attention. If Flight 14 succeeds, if SpaceX successfully launches Starship to orbit, deploys Starlink satellites, and catches the upper stage from the sky, it will definitively prove that the economics of spaceflight are about to change. A fully reusable super heavy lift launch system, capable of launching once a month or more frequently, would reduce the cost of orbital access by orders of magnitude. It would make routine space operations possible. It would unleash economic and scientific activities that are currently constrained by launch costs. For the first time, the limiting factor for space activities would not be the availability of launch vehicles, but the availability of payloads and the ingenuity of the people designing what to do with access to space. The potential failure scenario is also worth considering. If Flight 14 fails, if the vehicle loses control during re-entry, if both stages are destroyed, if the tower catches mist and the upper stage crashes, what happens next? The answer is straightforward. SpaceX continues. They analyze the failure, determine what went wrong, make changes, and try it again on Flight 15. This is the culture that has defined SpaceX since its founding. Failure is not the end of the program. It is data that informs the next iteration. This philosophy, while sometimes controversial, has proven remarkably effective. The Falcon 9 rocket succeeded because SpaceX was willing to test, fail, learn, and immediately try a better approach. Starship is testing this philosophy on a larger scale, with more powerful vehicles and higher stakes. But the core principle remains the same. Attempt ambitious missions, learn from what happens, and continuously improve. The engineers and technicians working on Flight 14 at Starbase are acutely aware of what is at stake. They have worked for months to prepare for this moment. They have checked and rechecked every system. They have modeled the mission profile thousands of times. They have prepared contingency plans for dozens of failure scenarios. They know that the success of Flight 14 will reshape the space industry. They also know that failure is possible, even likely given the ambition of the objectives. But they are proceeding anyway. This is the nature of frontier exploration. You prepare as thoroughly as possible. You mitigate risks where you can, and then you attempt something that has never been done before and hope that the preparation is sufficient. As Flight 14's launch date approaches, as the final inspections are completed, as the vehicles are transported to the launch pad, the anticipation will build. The entire space industry will be watching. Satellite companies will be thinking about their launch costs. Space agencies will be assessing their plans for deep space exploration. Investors will be watching the financial implications. And somewhere in South Texas, the largest rocket ever built will be standing on the launch pad, loaded with fuel, ready to attempt a mission that would have seemed impossible just a few years ago. When the engines ignite, when the vehicles rise into the sky and the booster and upper stage separate, when the upper stage climbs higher and higher toward orbital velocity, and the booster returns for a tower catch, and the upper stage enters orbit and deploys its cargo, the moment will represent far more than a single SpaceX mission. It will represent the moment when humanity's access to space fundamentally transformed. It will be the day when reusable orbital spaceflight transitioned from concept to reality, and it will be a demonstration that the future of humanity among the stars is not merely possible. It is already beginning.